Okay guys, I'm at the library, so I like not having to worry about my screen falling over. We are in section 1.6, factoring trinomials. First, tell me, why is it that the chicken said buck, 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 buck? Because the chicken didn't know how to say $2, $2. So it said buck, buck, give me $2. This has been a busy day. So that one was exceptionally lame. Factoring trinomials, as long as a trinomial is a degree of at least 2, you can factor every single trinomial that's out there. If you include complex numbers, which are those numbers that are the positive roots of negative integers, but you're not supposed to know how to do that yet, so we don't have to worry about those. But we do need to be able to factor over the set of integers. And you can use trial and error to find the factored form of a trinomial. Actually, a lot of the time, that's the only way that you can find it. This is one of those things where the more frequently you practice the skill, the better skilled you become at that particular activity. Something that is helpful for you to recognize, though, are perfect square trinomials. And these are examples of perfect square trinomials that you'll want to see. 2ab plus b squared, a squared minus 2ab plus b squared. And this one factors into a plus b quantity squared. First, let's see, does that all fit? Wow, I'm impressed. A plus b quantity squared, a minus b quantity squared. And these are called perfect square trinomials. Okay? There's a pattern that you recognize, and when you have a perfect square trinomial, the first term is a perfect square. The last term is a perfect square. And the middle term is twice, 2 times, the product, a times b, of the square roots of the first and last terms. Okay, and that might not make a whole lot of sense to you right now, but what you have right here is a plus b plus 2ab plus b squared is a plus b squared, which can actually be written as a plus b, a plus b times a plus b. Just like this could be a minus b times a minus b. This is a perfect square trinomial. This is the pattern that you want to be able to recognize, because all of your questions for this section should be, let's look up here and see it says, exercise A, the instructions are factor completely. Exercise B, the instructions are factor completely. Exercise C, the instructions are factor completely. Sorry. And I told the kids the door would be unlocked, and it's not. I am recording. Bye. You guys can go ahead and work on another topic of school, please, for 15 minutes. We can have a 15-minute further break and then come back. Okay. So with section 1.6, it's just going to be factor these things completely. So, example number 1 is going to be a perfect example, no pun intended, of a perfect square trinomial. And this is where the instructions say factor this trinomial, x squared plus 10x plus 25. And this says factor. And you remember that when you're factoring a trinomial, you are going to be breaking that up into 2 binomials that when you multiply them together, it results in a trinomial when you have this trinomial that you're factoring. Now, what did I just say that the pattern was? if you have a perfect square trinomial? Well, the first term is a perfect square. Well, that's true. And the second term, the final term, is a perfect square as well, right? So if we had the first term's a perfect square, the second term's a perfect square, the center term has to be 2 times the product of the square roots of the first term times the second term. So what's the square root of the first term? It's x. What's the square root of the second term? It's 5. Well, what is 2 times the product of the first and last terms, of the square roots of the first and last terms? 2 times 5, 10x. So, this fits our pattern. X squared plus 10x plus 25 is a perfect square trinomial. So that factors into actually, this could be x plus 5 the factors are going to be identical with perfect square trinomials. I really sort of got a little bit ahead of myself doing this. So, I'm going to say that the factors of perfect square trinomials are identical. Factors of perfect square trinomials are identical. And since a trinomial is going to factor into 2 binomials, if those factors of perfect square trinomials are identical, that means you're going to have, for your answer, a binomial that is used as a factor twice. Okay? And what this is going to be is the square root of the first term plus or minus the square root of the second term, used as a factor 2 times. How do we determine if this term here is positive or negative? It's the same as our center term. Okay? So when we factor x squared plus 10x plus 25, our answer is x plus 5 quantity squared. And the way that we verify this, x plus 5, the quantity squared, is equal to x plus 5 times x plus 5. If we FOIL, let's see if this is showing. Yeah, it's still showing for a little. You have x squared plus 5x plus 5x plus 25. X squared plus 5x plus 5x. This becomes x squared plus 10x plus 25. So remember we said that the way that you identified the perfect square trinomial, the first term's a perfect square, the last term's a perfect square. And the center term is twice the product of the square roots of those terms. There's a teaching video out there from last year in Algebra 1 that I'll send you guys the link to as well. I don't want to beat this problem to death. Okay. Just want to sort of step on it and squish it around a little like a bug and get it to death. Example 2, factor 4x squared minus 28x plus 49. Okay? Actually, the first thing that you should do is check and make sure there's not a common monomial factor. And they'll bring that up as soon as we're done with this problem. But I have 4 is not a factor of 49, so there are no common monomial factors. So the first thing that I want to do when I'm looking at this is say, is this a perfect square trinomial? How do I know? Well, the first term has to be a perfect square, which it is. The last term has to be a perfect square, and that's true. And this center term has to be 2 times the product of these square roots. 2 times 2x times 7. 2 times 2 is 4, times 7 is 28x. 28x. So yes, 4x squared minus 28x plus 49 is a perfect square trinomial. Where did I throw my eraser? Perfect square trinomial. So we've identified that this trinomial here is perfect square trinomial. That means that we have a binomial product that is used twice. The first term of that binomial product is the square root of the first term. So that's square root of 4x squared is 2x. The second term is the square root of that last term. Square root of 49 is equal to 7. Is this going to be a negative or a positive sign in here? Well, it's going to follow the pattern of your perfect square trinomial. Because we have to have, when we multiply 2x times 7 to give us 14x, and we double it, it has to equal negative 28x. The way we do that is by keeping the same sign as we have here. So this is all the work there is when your instructions say factor 4x squared minus 28x plus 49, because you have recognized this to be a perfect square trinomial, and this is how it factors. And I think I've said this in another video, but I've probably said, I know I've said it in Bible with relation to God's Word as well, but counterfeiters learn to recognize counterfeit not by studying a bunch of wrong things, but by studying genuine currency and saying, okay, this is true. You know, this is what real stuff looks like. This stuff looks different from it. Therefore, this stuff that looks different is wrong. Well, how do you recognize the stuff that's good? You've got to practice. You're not going to recognize perfect square trinomials unless you do some practice. So that's what this section is all about. Now, let me go ahead and write this down. What's our methodology, or what's the algorithm? Sometimes you'll hear said, if we want to factor trinomials, first thing that you want to do is factor out common monomial factors. Common monomial factors. And once you've done that, you know, that's like the GCF. You're going to take out the GCF in your trinomial. Then you're going to look for special cases. A special case might be perfect square trinomials, difference of 2 squares. Look for what? Special cases. And what's our next thing that we want to do? Then it does come. We have to, once we've used all of our special cases, factor by trial and error. The more you factor by trial and error, I promise you, the easier it is to do. Think about the first time that you went swimming. You had to think about every little stroke that you made, every little kick you made, or the first time you made chocolate chip cookies, you had to be real specific about making sure you followed every example. I mean, every step in there, and Mom had to show you how to turn on the beaters and how you don't take the beaters out of the bowl when the power's turned on, or else you have a big mess cleaning up your kitchen. The more practice you got, it was, you could almost make chocolate chip cookies in your sleep. You can swim with your eyes closed and singing or something. The more that you factor by trial and error, the more practice you have, the easier it will be for you. And finally, you have to keep factoring until every factor is prime. Every factor. And that might seem really like some strange terminology. You might not be exactly sure what's going on there. But if you'll just keep on factoring and factoring and factoring out, like for example, if you had 2x plus 4 times 2x plus 6, it doesn't work because before you had factored the trinomial, you didn't take out this common factor. So you've got a common factor of 2 in every bit of this that you wrote as your answer. And you'll see as we work through problems what it means to make sure that you keep factoring until everything's prime. All that means is factor completely. And we emphasized a lot last year, factoring completely. Okay, example. Factor x squared minus 4x minus 21. Okay, to factor by trial and error, your book tells us factor the first and last term, select the factorization whose outer and inner products add up to the middle term of the trinomial. Okay, well what does that mean? Let's look at this. We want to factor x squared minus 4x minus 21. So the first thing we want to do, is there any common monomial factor in here? No, there's not. Is this a special product? It's not a perfect square trinomial, that's a square, but that isn't. So no, there's nothing special. But we do know that we have, when we factor this trinomial, it will factor into the product of two binomials. And we also can tell that the signs of these binomials are going to be opposite. And how can we tell that? Well, we look at the sign of this last term. If the sign of this last term is negative, we have to have oppositely signed binomials, because this last term here comes from the product of the last terms in these binomials. So we have to get positive times negative to give us a negative answer. Now, what are we going to do? Well, we can look, and we're going to factor this first term right here, x squared. X squared is x times x, so that belongs right there as the first term of our binomial products. Now, what we have to come up with is, what factor possibilities do we have here for 21? Well, you can say 1 times 21, or you can say 3 times 7. No other way to factor 21. And you notice that this doesn't have to be prime factorization. Sometimes it won't be factored prime, and this time it is. But what you're going to do is say, I have to have some combination of these two factors, so that when I add them together, I end up with this center coefficient here. We have a central coefficient of -4. So we want to have some combination of factors here that gives us a -4. Well, there's no way adding or subtracting a 21 and a 1 that we're going to end up with 4. But 7 and 4, I mean 7 minus 3 is 4. So 7, a positive 7 and a positive 3, that doesn't do us any good, because that equals 11. A -7 and a -3 doesn't do us any good, because when you add those together, you have a -10. A -3 and a +4 doesn't work. I'm sorry, I put part of the answer. We know that it's not going to be 3 times 7 immediately, because those signs have to be negative, so we don't even have to worry about both positives or both negatives. So the only other two combinations we have of possible factors would be +3 times a -7, -3 times a +7. It just doesn't look right to me. +3 and a -7, when you add those two together, you get the -4. When you add together a -3 and a +7, you get a Positive 4, I hope. Positive 4. What does our center term need to be? It needs to be a negative 4. So we need to have a negative 7 and a positive 3. So let's FOIL this back and see what happens. X times x is x squared. X times negative 7, negative 7x. 3 times x plus 3x. Plus 3 times minus 7 is minus 21. And then we're going to go combine those two x terms, so we have like terms. X squared minus 4x minus 21, which is our original problem. So our factorization, x plus 3 times x minus 7, is correct. And that's what you need to do to be factoring these trinomials. Okay. Let me go ahead and take time to quickly run through these two additional examples in the book. And then I'm going to give you just the link to some of the old videos, because my throat's getting pretty dry. Plus my kids brought me lunch and I'm hungry. Okay. Factor 12 x squared minus 5x minus 2. Do we have any common monomial factors? No. Do we have any special products? Is it a perfect square trinomial? No. So we've just got a mess here that we're going to have to factor. And I'm going to go ahead and step through all of their work here and see if that'll help you for me to say it and write it at the same time instead of you guys just reading it. Okay, there's no common monomial, so first we have to factor this first term. Well, we're going to factor 12x squared. So that can be 1 times 12x, 1x times 12x, or it can be 3 times 4 with the x's. It can be 2 times 6 with the x's. So we're just going to go ahead and pick some random pair of factorings for our binomials. So you could pick x and 12x, you could put 3x and 4x, you could pick 2x and 6x. So we're going to go ahead and pick 12x and x. And I probably would not tend to do that because when you're having to do things by trial and error, it's not typically the number times 1 that are factors. So that wouldn't be my first choice. I think they're picking this as the first choice here to show you, okay, we've tried it and it's wrong. So we have that. Now, what are we going to do? Well, we have to factor the last term. How can we factor the last term? Negative 2 and 1, positive 2 and negative 1. Why am I doing it this way? Negative 2 times 1, or 2 times a negative 1. The reason I did that is because this last term here is negative, so the factors are going to have to be 1 is positive and 1 is negative. So let's try trial and error. Plus 1 minus 2, or 12x minus 1 times x plus 2. What happens? We get 12x squared, but then we have minus 24 plus 1 minus 23. That doesn't work. So that one's wrong. We're going to get our minus 2. Negative 1 times positive 2 gives us the negative 2. Let's see if we end up with a negative 5. Well, you can tell here already you don't. 12 times 2 is 24, minus 1 is 23. So neither of these attempts here with the factorization of 1 and 12 work. Which, as I said, most of the time when you have large discrepancies or large disparity. It's not a discrepancy, there's large difference in the size of the factors. That's usually not what you're going to be looking for. So now let's try another pair of factors. My first choice is always going to be the two factors that are closest together. But once again, they said, let's see what happens if we try a 2 times 6. So we're going to have a 6x, 6x, and a 2x. Now we've got 4 possible choices here. We can do, let me see, we can do 6x plus 1 times 2x minus 6. We can do 6x minus 6 times 2x plus 1. See, we're still using the same factors, but we've got 6x minus 6. There are 2 more we can do. We can do, oh good grief, what are they doing? 6x minus, forget what I said here. Let's erase this part. Our factors here are not going to be 1 and negative 6. It's 1 and a negative 2. See what happens. And a negative 2. 6x times 2x, 12x squared. 6x times negative 2, negative 12x plus 2x. And at this point you stop. We're trying to get negative 5x. That one doesn't work. Well, let's try it in the other direction. 6x minus 2 times 2x plus 1. We still have our 12x squared. Now we have 6x minus 4x. Does that work? Does that give us a negative 5? Nope. So these 6x and 2x aren't working. Now we try 3x and 4x. And we know that our signs in these factors have to be opposite because we have this negative. So we're going to try a positive 2 and a negative 1. We still have the 12x. We have 3x times negative 1 is negative 3x plus 2 times 4 is positive 8x. Look at that. We finally get a 5x, except it's a positive 5x. So that doesn't do us any good. But we know that somehow we've got to have these factors have to be the ones that we need. So we want the 2 times 4 to be negative. So we're just going to change our signs here. Negative 2, positive 1. Let's see what happens. 3x times 4x, our outside term, is 12x squared. I'm sorry, our first term is 12x squared. Outside term, 3x times a positive 1 plus 3x. Inside terms multiplied together, minus 8x. Last terms, minus 2. 12x squared minus 5x minus 2, which is what we had originally. So we now have the factored form of 12x squared minus 5x minus 2. That took a while to get. I promise you, the more of these you'll do, the more you'll be able to recognize combinations. And this is a good example of why I have said from the beginning that it's so important when you begin algebra that if you don't know your multiplication facts, that you get those things down so that you say 7 times 7 is 49, 8 times 9 is 72, 9 times 9 is 81, so that there's no hesitancy. Because the more of this trial and error stuff that you can do in your head, the much less frustrated you're going to be. Okay, one final problem. The example is factor 30x squared, oh yucky poo, minus 305x plus 310, and you look at this and you say, don't like that. But first, right away, you notice that there's a common factor of 5 because they end in 5 or 0. Not a common factor of 10 because of this. So let's factor out 5, and that becomes 6x squared minus 561 plus 565. Let me make sure that I got that one right. And I did not get that one. It'll be about another 5 or 10 minutes. 65, 5 times 65 is 325. That should be 62 plus 62. Now, is there anything else that we have in common here that we can factor out? Well, the only factors of 6 are 2 and 3, 1 and 6. 61 cannot be divided by 2 because it's not even. 61 can't be divided by 3 because the way that you tell if something can be divisible by 3 is if the sum of the digits is divisible by 3. 6 plus 1 is 7, which you can't divide by 3. So that means that we are going to have to factor stuff here by trial and error. And I'm going to say, like I said, it's usually the two factors of that first term that are closer together. So I'm going to try saying 2x times 3x first instead of saying 6x times 1x. We have to have this same factor of 5 here. You can't drop that. But I'm going to put in as my trials a 3x and a 2x to begin with. 3x times 2x gives me 6x squared. Now, let's see, what am I going to do about these signs? We have a positive third term. We have a negative central term. What's the only way that we're going to be able to do this and still have a negative center term? It's going to have to be negative times negative, because a negative times a negative is going to give me my positive third term, and I'm going to be able to sum these two together to get a negative 61. If I had said one term was negative, one factor right here was negative, one was positive, when I multiplied the last terms together, it would be negative, but according to my problem up here, it has to be positive. So now we're going to have to do some trial and error here, which means we need to factor 62. Well, let's see, what can I factor 62 as? Well, something that jumps out to me right away is 62. I can divide, actually nothing's jumping out. That is 2 and 31. 2 times 31. 31 is prime. You can't do the division any further. We have to be able to come up with a negative 61. That really can't be what we're going to do. But it is. We want to have a negative 61. What happens if we put a negative 31 there and a negative 2? Well, 3 times 31 is already our problem. 3 times 31 is 93. We only have to get to 62. So that particular manipulation doesn't work. So let's just exchange those. Minus 31 minus 2. Okay. 6x, so we have minus 6x minus, okay, that should be 61x, minus 62x. Okay, that is not working either, is it? what does that tell us? It's going to tell us it can't be factored any further. As strange as that seems, this point right here is all the further that you can factor. Because I'm sitting here thinking, how in the world am I going to be able to get combinations of factors so that I end up with a minus 61 but a positive 62? I can't. So that's part of the challenge of factoring things completely. Go ahead and look through this example a little bit more. Try and study it and see if you can get a better understanding. But part of how you saw me going, is because you can't factor it any further. Now I will tell you that the majority of the time when you're doing your homework, you're not going to stop at this point. And especially if you had a test that said, you know, you had a bunch of these that you had to factor completely and you kept saying, can't be factored anymore, can't be factored anymore, can't be factored anymore, you're missing something. But something like this is only going to show up occasionally. And here we have, you know, this term, this trinomial factors into 5 times the quantity 6x squared minus 61x plus 62. That's the end of section 1.6.